Hello and welcome back to our discussion of forecasting. In our last video, we talked about how we can implement the moving average forecasting technique, and also we talked about the exponentially weighted moving average or exponential smoothing method. Not only did we implement those two techniques, but we also assessed the quality of the resulting forecast by looking at some forecast error statistics. In this video, I want to continue our conversation and introduce a third forecasting technique, that is time series regression. Now notice that I emphasize that we're talking about not just any kind of regression, but time series regression, as opposed to causal regression. In causal regression, is we try to learn about and understand the drivers of demand. For example, I can argue that demand will be impacted by income and population levels, and accordingly I would then develop a forecast based on my projected income and population levels in a certain market. So those projections would then define my expected demand in a future period. Now the thing about causal forecasting is that it's actually fairly hard to do for a number of reasons. Number one, it takes quite a bit of statistical knowledge to do it properly. Remember, as always, garbage in, garbage out. If you misspecify the model or you do not properly estimate the model, the result you get is garbage, and as a result, the forecast you get is garbage as well. So that's one problem. It's simply technically somewhat more challenging to implement causal regression properly. Second, it takes a lot of data. Remember, if you want to predict demand for a certain product or a certain store or a certain market, you'll need a lot of data on that store, on that product, or that market, such as local income and population levels, for example. Information on competitors' prices, and so forth. So it takes a significant amount of data, and that tends to be hard to come by, which is why it is often not all that practical to pursue causal regression in forecasting. The good news about time series regression is we don't worry about the drivers of demand, and we simply develop a forecast based on our observation and analysis of past demand. So in other words, we're simply taking manifest demand observations and we try to fit a linear or nonlinear regression line to that past demand observation and then extrapolate and thereby come up with a forecast for some future time period. Now let's go back to the data. The graph that we're looking at is the plot of the data for the 100 weeks that we have, starting from week 12 all the way through week 111. And again, our objective, of course, is to come up with a forecast for period 112. Now the good news is it's quite easy to implement time series regression forecasting in Excel. There's a number of ways we can do this. We can either use the data analysis 2-pack function in Excel, or we could even do it graphically right here within this graph of demand data that we're looking at, which is what we're going to do now because it is really quite nice to visually illustrate what it is we're doing here. So let me simply go into this graph, and I'll place my mouse over any point on the line. It doesn't matter which one you pick. Then you right-click with a PC or control-click with a Mac, and then select Trend Line. So you get a pop-up window. And at the same time, notice how the linear regression function is being fitted to the data. Notice that this line, of course, is a line that minimizes the sum of the squared residuals. That is the sum of the squared distances between the regression line and the actual demand observations. Now, if I look at this linear regression model, it is plain to see that I probably wouldn't do such a great job for forecasting for period 112 if I use this linear regression model. The simple reason being, if I just look at this regression line here, notice that my forecast for period 112 would probably be somewhere around, let's say, 560 or 570 units. But the problem is this linear regression function doesn't adequately capture the cyclicality in the data. Or in other words, it doesn't capture the fact that the trend has reversed and now we're on a downward trend. So in fact, if I just look at the data, I would expect demand in period 112 to be around 400. So the linear regression model here just doesn't provide a good fit with the actual data. The good news is regression models can be very flexible. In other words, I don't have to restrain the regression function to be linear. What I can do is I can allow it to be polynomial. So we're going to select a polynomial regression function here, and I'll select polynomial in the pop-up window. So right now you see we get a polynomial model to the order of 2. All this means is we expand our linear model by adding a square term, and that's why it's order 2, or in other words, a second degree polynomial model. Now I can add another term here. I can have a third degree polynomial model. Now you can see I get a line that really seems to fit the data extremely well. So a third-degree polynomial model implies that I have a linear term, a square term, as well as a cubic term. I could of course keep going here and add some more terms to it. Notice that every time I go to a higher order model, there's a slight change in the shape of the regression model. But for all intents and purposes, I think we're well served with a third-degree polynomial model. So that is what I'll be using here. Again, the great thing about this type of polynomial time series regression analysis is I can make my regression function flexible enough to pick up patterns such as cyclicality that is clearly present in the data here. Now I'll indicate that I want to see the equation on the chart as well as the R squared. And then I click OK. Now let's take a look at what we get here. First of all, I get an R squared of 0.85. Remember, this means that the model explains about 85% of the variability in the actual demand data. This is phenomenal if you ever manage to pull off a forecast that explains 85% of the variability in the data. You're probably on the right track, and you'll probably earn a pay raise. So clearly this is a great indication that this forecast model will perform extremely well. Now let's take a look at the regression equation. This should look familiar in that all regression models that are linear in parameters, such as this one, follow a similar structure. We have an intercept term that here is shown at the end is 252.79. Then we have this linear term that is a coefficient of 4.4112. We have a square term with a coefficient 0.0604, and finally we have a cubic term with a negative coefficient. So again, notice we have three elements here besides the intercept, and that's why we have a third-degree polynomial model as we just specified in Excel. Now I want to show you how we can develop forecasts in sample forecasts and out of sample forecasts by using this particular regression model. So what I'm going to do is I'm going to write out the various parameter estimates. So this intercept is 252.79. The coefficient for the linear term is 4.4112. The coefficient for the squared term is 0.0604, and the coefficient for the cubic term is negative 0.0009. All I need to do is now is to implement this particular regression function for the various periods. So let me show you how to do that. I'll start at my first period here. This is week 12, and the forecast based on this regression model would now be equal to the constant term. Make sure to lock in the cell references. Plus now I'll take the coefficient of the linear term, lock that in, times the number of the current time period. Now here is one of the many imperfections about Excel, unfortunately. Notice that I'm looking at week 12 right now, but when Excel specified this regression model, it simply assumed that my first data point here is period number 1. So I want to multiply this coefficient for the linear term with 1 as opposed to using the actual number of the week, which is 12. Again, I should be able to simply use the week number, which is 12 over here, but if I did that I would get gibberish in terms of the results. Excel kind of ignored the values in the x-axis when it fitted the model, which it really shouldn't do, but that's just how it is. So I'll add to that row the squared term. I'll take the associated coefficient and multiply that by the number of the time period, 1 in this case squared, and finally I will add the cubic coefficient and multiply that by the number of the time period to the power of 3. Now you see the regression forecast for week 12 would be 257. Notice this is simply the point on the regression line for week 12, 257. I can now go ahead and simply copy my calculations all the way throughout the remainder of the data set, and you see I get a forecast for period 112 that is equal to 387. Now clearly if we go back and look at the graph, you'll see, well, that looks pretty good. That's what we should probably expect for demand to be roughly in week 112. Visually, this seemed to be a pretty good estimate of what demand would be. But of course I can again calculate my forecast error statistics. As usual, I will take actual demand observations and subtract from it the associated forecast, and I'll look at the absolute value thereof as well. I'll copy all this down throughout the remainder of the data set, and that will allow me to calculate, as always, my forecast error statistics. First, the mean absolute deviation. So you see I get 31. And for the mean error, I will get a value of 0. So let's talk about this just a little bit. Remember, the mean absolute deviation tells me that on average, my forecasts are off by 31 units in either direction. And again, it doesn't tell me whether I tend to under or over forecast. It just tells me about the magnitude of the forecast errors. The mean error is 0. And in fact, this is not surprising. If you implement a regression analysis properly, it will always be 0. And the reason really is quite simple. Remember that this regression line is specified in a way so as to make sure that we minimize positive and negative deviations, or the sum of positive and negative deviations. In other words, as it turns out, the sum of all positive errors will be equal to the sum of all negative errors. And that, of course, implies that I'll have the mean error of 0, which is why we say that time series regression analysis yields unbiased forecasts. Again, I'm biased because the associated mean error will always be 0. So if I look at these forecast error statistics, I'll of course conclude that out of the 3 options we looked at here, time series regression will be best. In other words, I will get the lowest possible forecast error statistics comparing these 3 options. There's just one note of caution I want to advise you of, that's sort of a little skewing my judgment, I guess, in favor of regression analysis. Notice that when I develop forecasts, let's say that you're using the moving average, notice how I develop every forecast for every period in the data sample based on my knowledge of past demand only. The same was really true with exponential smoothing as well. I always calculated my forecast as a function of prior period demand and the forecast for prior period demand. Now in regression analysis, this is not true. Notice that my forecast in any given time period is based on one and the same regression model, but that regression model was of course fitted based on my knowledge of the entire data set. In other words, you could argue that all of these forecasts here, they actually have a forward-looking component because the regression model was in part defined based on my knowledge of future demand. That's why I'm saying clearly it's not surprising I'm getting the best forecast result if I use regression analysis. But that's because I'm basing it on a model that is fitted to future demand observations as well. This concludes my discussion of the forecasting techniques that are moving average, exponential smoothing, and time series regression. And remember, as always, if you have any questions, please feel free to ask. Thank you for watching.